Hello, everybody. Welcome to today's digital event, Delivering Net Zero Buildings Through Passive Design. My name's Kelsey Kolvenschlag. I am the Sales Operations Manager here at ArchVision. I'm joined today by Peter Krebs, one of the founders of Sefaira. Today, we will be doing a presentation followed with a live Q&A. We will have the chat open, so please feel free to put questions in there as we go along, and we will do our best to get to all of them at the end. Peter Krebs is a founder of Sefaira, which has been part of the Trimble SketchUp since 2016. He has led sustainable design and passive design projects, starting with the Solar, the first LEED gold building in New York City in 2003. Today, he'll be showcasing through a net zero design project the way Sefaira delivers optimal energy analysis. And with that said, I'm going to turn it over to Peter.
Hey, thanks so much, Kelsey. Appreciate it. Let me see if I can share my screen here and we'll get started.
All right, you're good to go.
Fantastic. All right. Well, thanks, everybody. Appreciate you joining today. We're going to be covering a project called the Iowa Nest Residence in Iowa. It is a net zero energy build, and the focus is really on the process of delivering net zero energy construction and doing so actually at conventional cost. So there's I would say, misconception that has existed for years about the cost of sustainability and the fact that there's a premium associated with sustainable design. Now, while that may have been true 20 or 25 years ago, modern designs are tending to meet, in some cases, even beat the costs of conventional stick-built construction, yet deliver far more significant and impactful outcomes. So if we're talking about delivering a building that is climate positive, that generates its own energy, that has a very, very low energy footprint in operation, we're going to cover how we do that. And we're going to cover the methodologies and some of the building physics to get you familiar with the process of delivering net zero energy buildings. So this project is going to be looking at 5 early design studies, 4 cost-saving strategies, and ultimately a total of 9 years of data. What we're really trying to understand here is using the tooling and the workflow, the approach for net zero design, since this is something that can be translated not just to residences, but also to commercial buildings, to institutional buildings, and a broad variety of projects worldwide. This has been in use. I think in Sefaira, we have well over 500,000 buildings that have been analyzed and design studies that have been done. So it's really exciting to take this approach. It's very logical, and hopefully by the end of this conversation and webinar, you'll get a much better idea of the way in which this can happen and how iterative the process can be. So it really comes down to a couple of factors. First and foremost, we're talking about loads and how do we reduce the loads of the projected design. Then we're going to look at reducing demand. And then ultimately, kind of the cherry on top is adding renewables to be able to power the building that you're then designing. So if we look at this, we need to start really with the definition of what loads are. Ultimately, if you strip away all the thermodynamics and everything else, loads is the amount of heat you need to add or to remove from a building to keep it comfortable. Now, comfort means different things to different people. Certainly what temperature ranges we're comfortable with, let's say in the United States, will be different from those of Western Europe or Southeast Asia or Australia. But what we do know is there are certain comfort bands, and we want to operate within those based on the purpose of what that project is. So a residence may have a tighter tolerance than, for example, a commercial building or vice versa. So first, we start out with heating load. Heating load is the amount of heat we need to put into a space to keep it comfortable in those winter months. And cooling load, obviously the opposite. It's the amount of heat we need to remove or reject from the building, also to keep it comfortable. But if we set a goal of reducing the total amount of heating and cooling as much as possible, we can actually optimize for the smallest possible load footprint in that project. So to talk about these heat gains and losses, we actually need to come up with some definitions. So I promise I won't go more detailed than this, but we need to start by thinking about how heat enters a building. So there are a number of different means by which this happens today. You've got solar gain, that's sun coming into the building and warming the space. You've got conduction, that's literally sun affecting the skin, the envelope of the building that you're in, and heating that up. We've got infiltration, right? So that's the warmth of the air that's coming into the building, that's infiltrating into the interior air. We've got ventilation. So those are actual heats that's generated in the process of providing fresh air and cooling into the building. Well, some of that heat is going to come in as well. Then we look at appliances. So if you look around you in the room you're in right now, I guarantee you that appliances or equipment, whether that's a laptop computer, whether that's a microwave, whether that's a refrigerator, these are all devices that are producing heat. And often, even if they're a low energy appliance, they are producing heat over a very long duration, right? Your refrigerator might be running, you probably have it running 24/7. So if you can reduce the load associated with that, you're also reducing your cost to operate it and also the amount of heat you then need to do something with in that space. And there's lighting. We've come a long way from the days of incandescent lights. Most lights nowadays are sold as LEDs, and those have a much lower amount of wattage for the amount of lumens, the light that they produce. And the last piece is people. People produce heat. We produce anywhere between 70 and 90 watts of heat energy. And so while there are different sizes of people and different ages, the reliable thing is if you know you have a lot of people in a space, you will be generating heat and you need to do something with that heat. You may want it at certain times of the year, but you may want to reject that heat in other times of the year. The contrary to this, of course, would be how does heat leave the building? Well, when we talk about heat leaving the building, those losses tend to be through conduction, again, through the envelope itself. They can be leakage related. That's actually the warm air, if you want to think of it that way, exiting the building through gaps in your windows and your bucks. It could be warm air that's leaving through the base of your door. And there are just so many porous areas within a building that reducing the overall amount of infiltration and therefore the leakage as well can be a really meaningful step to reducing the total loads you need to design around. Last piece, of course, is ventilation itself, right? Anytime you bring air into a space, you may need to condition it so you get the benefit of the fresh air, the fresh oxygen, but you're still doing something with the heat or cool that it had. So that gives you an idea of loads. How do you go about this, though? So what we've created within the Sefaira platform and the SketchUp platform is really a series of tools that starts with the performance of climate analysis, even before you have a massing, then moves on to comparing conceptual design massings, really to optimize them for loads, and then finally to look at groups of these different strategies and to optimize the sum of those or the assemblies themselves. So very briefly, for those of you that have SketchUp today, SketchUp includes something called pre-design. And pre-design allows you to test out how climate will impact your potential design. So as you look at a building, even before you have a geometry in place, you can start to test, for example, what the effect will be of orienting that building, or what are the potential strategies we want to consider given the climate in the place you will be building. So is this a climate that is going to promote natural ventilation, or maybe natural ventilation isn't an option there? Is this a climate where shading could provide a meaningful benefit to the occupants? Is this a place where you could have more of an indoor-outdoor space, or where you're constantly conditioning the space to make it habitable and comfortable? Another option and question we are often asked is, how do you apply shading strategies to be able to reduce the amount of heat that's coming into a building? So you can test different facade shading strategies, whether those are overhangs or brise soleil or other design options, to protect your space from light coming in and therefore you gaining heat in the process. So that's part of pre-design, which is part of every SketchUp subscription. The second half of this is Sefaira. And Sefaira is a conceptual energy modeling tool and daylight modeling tool that lets you test out different massings. So it lets you try different options and to compare them side by side. So we can see how a building would perform in, let's say, one specific set of conditions with a certain loading, with a certain number of people in it, with a certain watts per square foot of light or watts per square foot of equipment density, and see how that compares with another building that has a different shape, a different morphology, a different design. They may have exactly the same square footage overall, but they may have dramatically different performances. And tying and testing those against one another quickly and iteratively is really the heart of early stage concept design. And that's how our customers get to the best possible results. If you go beyond energy, you can also do a comparison of conceptual massings in daylight. So you could say, we're going to put energy as a metric aside. What is the best possible design, for example, our window to wall ratios, to give us the option to look at different window types or different shading options, in so doing, reduce the amount of artificial light we need in the space and maximize the amount of natural light that's coming into the space. The office I'm in right now, there are no artificial light. There's no artificial light at all. It's entirely naturally daylit. That makes it a very comfortable space to be in. We find when talking to end users, that that's the kind of environment that they're trying to replicate for their customers. As much natural light as possible without excessive glare. As you get further in the design process, you can start to optimize assemblies. Assemblies in our world would be structures or groups of different systems, as well as different efficiency measures. That could be types of glazing, that could be types of insulation, that could be a certain amount of infiltration, for example, that helps us understand what does the overall package look like from a cooling energy budget, from a heating energy budget, and from an EUI, or energy use intensity, just a metric that gives us a direction, a trajectory of how much energy we'll need to keep that space within the parameters we set. We can compare things like energy costs. Annual energy cost is a common one. And you can try out different options or packages of options relative to a baseline. Typically, that's done relative to code baseline. So we can see how many percentage better you are than code baseline, how much potential savings you might have. But the fundamental idea here is to do things quickly and to do things iteratively. Try different options out. Don't try to preen those different solutions too soon. Try things out, see what the data tells you, and then based on the data, pivot and make adjustments to the overall design to get your EUI down, to get your annual energy cost down as well. So if we think about why and leading with why, the reason we do it in this order is that if we can get to lower loads, right, that allows us to meet the requirement within the building, the heating and cooling requirement, with smaller systems. Smaller systems also happen to cost less. They're often simpler to maintain and run. And so there are benefits that come along with having lower loads downstream of the actual load itself. Smaller systems also require less energy. And when we have less energy demand, that means we're actually projecting a lower operational cost and operational carbon over the course of the lifetime of that building. Don't be thinking about a building from an annual perspective, thinking about it for its lifespan and whether or not it might be reused in a different purpose in the future. And if you follow all those pieces, then the renewable component, the way in which we generate the energy to power that building, will be the most efficient possible, because you'll need the smallest footprint of, for example, solar panels or wind to be able to deliver the energy needed to drive the building. So that kind of gives you the lay of the land, the approach that is taken. And we've worked with thousands of different designers, sustainable designers across the world. And the consistent message we get is, if you follow this approach, this formula, this direction, that strategy will get you to a low energy or a zero energy building. What better way to look at that then than to look at this specific project? This is a project called the Iowa Nest. And just to situate yourself, this is a very rural area of Iowa. This actually used to be a quarry. And since it was abandoned in the 1980s, this has become a very mixed use area. So you've got pastures, you've got woodlands, you've got set-asides, and it's a very beautiful area. When the client came to speak with us about how to deliver this design, the objectives were manifold. First of all, deliver a building that could outlast them, and ideally last for over 100 years. The second is deliver a building that could be as passive as possible, So using the benefits of the location of where the building should be to maximize the benefit of the shade, to use thermal mass to benefit, and ideally to leave the smallest possible environmental footprint upon its completion. And then the last piece was something kind of nuanced, which is how do you deliver a building that has the lowest overall ongoing maintenance? So as the building is lived in, how can you deliver a building that's going to be as easy to maintain and to run and to operate with as few things that could possibly break over time? So this was brought to one of our customers, Sterner Design, and Sterner Design started to use Sefaira for the purpose of doing this analysis. So one of the first questions that came out is, in this kind of a residential structure, roughly 2,000 square feet of square footage, what strategies would make the most impact to the building itself? So Sefaira was used to develop a list of potential strategies for the box model that was shown, and just say, okay, we don't know if this building will look like what is shown, but at this stage, all that matters is a relative importance of which strategy will impact the building the most, and which strategies will impact it least. And so the width of the bar here shows the impact. You can look at something like glazing ratios, for example, or natural ventilation or thermal mass. These are factors that are passive features, right? We can set them early in the design process, and they have a outsized impact on the building's performance relative to that vertical line. That vertical line is the code baseline for the state of Iowa. Now, if you layer on that strategy, whether or not that is going to be inexpensive, $1 sign, or very expensive, $3 signs, you can then start to ask which design strategies are most cost effective. In this particular case, you look at something like glazing ratios, and that's a low-cost strategy that has a big impact. So the owners here decided that that would be one of the strategies to go with. Same thing with natural ventilation. It is an impactful strategy that can be delivered at relatively low cost. Other strategies considered that were in this category were things like thermal mass and reducing the amount of infiltration. So these are, again, strategies that make a big impact at a low cost before we get too far deep down the rabbit hole of the design. So what Sterner Design did next was to test a couple of these conceptual designs. Letting the architect do what they do best, they came up with and ideated a number of different design options. And some of the most top ones are listed here, just to give you a visual. So what you see is a hand sketch and then a broad floor plan for each of these design approaches. And then below that, the SketchUp box model with the Sefaira daylight analysis on top of it. So this is one of the available tools within Sefaira, is to be able to visualize through the building where the light is going to be incident, what part of the buildings are going to be well lit versus overlit versus not so well lit. And so in this case, the darker areas are areas that aren't getting a lot of natural daylight. The areas that are brighter colors are getting a good amount of natural daylight. And the bar you see below there, the SDA, stands for spatial daylight autonomy. There, the higher the value, the more natural daylight you're getting. So clearly a couple of these options, the pavilions option, the peninsular option, the terrace option, those stand out as providing a really good quality daylight. And the number below those are the EUI, the energy use intensity. So there we're looking at what is the lowest amount of energy per design that can yield this result. If you're curious, the size of the bar underneath it, for example, the red bar is the amount of heating required to keep that space comfortable. The blue bar is cooling, the green bar is domestic hot water, and the light blue bar is appliances. So just to give you a relative performance of these options. So one option that stood out, and we saw that in the previous slide, was looking at natural ventilation. How can natural ventilation be used in the design to be able to promote a good cross breeze in the space and to potentially avoid mechanical air conditioning? Separately, since there are long winter months in Iowa, What are strategies you can use to use and consume as much of that light that comes in to warm the space up? And during the summer months, design a shading system to reduce the amount of heat that comes into the space. So these are the questions that were asked and that we wanted to test. To answer that question, we really need to think about the glass not so much as being something that's just visually appealing, but actually, is it promoting or is it productive towards our goal? So this is a box model of one of the designs, and it gives you an idea of how the building performs in heating season, so that's winter, and on the right-hand side, in cooling season, that's in the summer. And so the objective here is, do we get good light to come in to warm the space up when we need it most, which is in the heating season? And the answer is yes. You see lots of bright patches show up there across the space, upstairs and downstairs, in the heating season. Meanwhile, in the cooling season, in summer months, you actually want to have a much more diffuse light. You don't want direct light to come in because that direct light is heating your space when you don't want that. So coming up with a shading system to mitigate the amount of those areas that you don't want to have warmed is a really interesting part and something you can easily test within Sefaira. Ultimately, for this particular design, this gives you a breakdown of how the shell was designed to be able to maximize shading in an intentional format. What do I mean by that? The intentionality here was using this roof design to shade the upper floors during the summer months, where we really didn't want to have additional light come in to heat the space. And to provide an additional brise soleil here on the bottom and a shade that reduced the amount of light that came into that lower living room area and the kitchen and dining areas. So you can test these things out, and you can test them quickly if you allow the software to test these different attributes. So one of the best ways of communicating this to the design team is by looking at a waterfall chart. And this is a popular chart from many of our customers, looking at what are the reductions over time associated with each strategy or each group of different design interventions. So the left side of this graph shows actually code baseline. This is what a standard building would look like. So a standard residential building, I should be specific. And then next to it, you can see each individual intervention. For example, applying a high level of insulation, in this case, roof, wall, and floor insulation, had an impact of reducing our total energy use by 20%. That's a really meaningful thing. If you did nothing else, that is a great passive design measure. Being intentional about infiltration, and this project was designed around the insulated concrete form approach, or ICF approach, that reduces that annual energy use by another 21%. And then being intentional about where and what kind of glazing is used, and the use of thermal mass, i.e. concrete in this space, that gets you down between those first four strategies to over 50%. So again, with nothing else, those first passive design measures are reducing the amount of overall energy use by over 50% compared to baseline. And at that point, all the actual efficiency strategies, so a lower lighting budget because you can use LED versus incandescent, for example, or more efficient domestic hot water fixtures, those are strategies that have a much smaller overall efficiency, but you're doing it on a much lower set of loads already. So the impact is greater. You combine that with avoided mechanical cooling, and even in this case, looking at a ground source heat pump, an ERV, those are mechanical strategies that take you that further step down. And ultimately, this building was able to deliver almost an 80% reduction relative to overall annual energy use at the baseline level. What this tells you is now you're in spitting distance to be able to deliver this building with a local energy source. You can use renewables, in this case, solar PV, to deliver the energy you need for the year to power the building. And that's what makes it net zero. As you can see, if you had none of the strategies on the passive design side, that would mean you'd have a far larger solar PV array to be able to power the building. and achieve its goal. So reducing loads and then being efficient about the systems you do use allows you to be far more specific about the total size and reduce the total size of the solar PV needed to power. So, as I said earlier, there are a couple lessons that were learned. And so I want to share some of these with you. The first design, and this is one of the earliest designs, in the SketchUp model you see on the top, this was a comparatively more complex design. And one of the things we found is in the process of specifying the insulating concrete forms, corners matter. The more corners one has in this particular case, the more complex the system is, and it actually results in a higher cost. The design on the left is over twice the budget that was initially presumed. Meanwhile, the design on the right both is simpler, which means simpler to build, but also it is simpler and cheaper to operate. So this is a lower cost build on the right-hand side, and also uses 10% less energy than the footprint shown on the left. So this is a clear case of testing out different geometries, different massings, and being able to see what their operational cost impacts will look like. The second lesson, now that you have a simple geometry, keep the envelope simple. The solution that was devised, and this is a cross-section, this is a picture from LayOut, which is part of the SketchUp application. This is the design documentation tool that SketchUp provides. This gives you a really clear view as to the way in which everything is composed within the building. You can see the walls and floors made out of concrete. You can see the roof made out of concrete as well. And also you can see in model, in this case, what are the insulating concrete forms? That's that hashed color. And then the light deck. The light deck is the roof supporting system that has insulation in it and acts as a structural support for the concrete while it's curing. This simple envelope meant it was simpler to deliver, and simplicity means cost savings. The next piece is using something called integrative design to reduce the overall HVAC costs. So if we were to compare the cost to install a conventional HVAC system in this building, let's say it's roughly $25,000, that's the option on the left. It's split, let's say, evenly between cooling and heating. Well, in a design optimized for lower mechanical usage, you can get to something like a ground source heat pump plus an ERV, an energy recovery ventilator. That's the option in the middle. And the reason that that dashed section is on cooling is because cooling isn't required, or I should say, it can be greatly reduced if you need cooling at all. More of a focus is on dehumidification than it is on cooling to keep the space comfortable. And so you see this ventilation component show up in green as opposed to the cooling, which is in blue. Ultimately, by looking at the mechanical design and testing this within Sefaira, we were able to determine that actually a ground source heat pump would be overkill for the project. It would be too much overall cost, but also it would deliver too much heat at the time that it wasn't needed. This building doesn't require a lot of heat. It is so well insulated and so low infiltration. So the actual delivery, when all was said and done, was an electric radiant floor system. So that can be toggled on demand on a per room basis if needed by the client, and an ERV, and the energy recovery ventilator is there primarily to bring in fresh air and to remove deoxygenated air out. Another area is to focus on being really judicious with expensive finishes. If you look at where most dollars go in the construction process, when you look at the overall build, and we'll look at a cost breakdown for this house in a moment, the finishes side of things, whether those are in bathrooms, floors, kitchens, they tend to be the things that really drive up cost. So if you can reduce the amount of space you need for a bathroom, you can still have a high quality finish, but you're not putting as much of it on. Less finishes by square foot means less cost. And I've seen a picture recently of this same space, the actual real, the reality compared to the rendering, and it looks exactly like it without the wood floor there on the bottom underneath the tub. So even farther use of finishes and making sure that that dollar you spend on a finish is going the extra mile. Details matter. This is the last piece of this puzzle. And the left-hand side shows a breakdown. Now, Starter Design did an amazing job of actually designing the entire construction, almost like a Lego instruction book, down to the detail. These are actual documents produced in layout that walk through every piece of the puzzle. So this was something that could actually be built following the strict instructions and focusing on things where they really needed to be. So things like the details around the ceiling, the taping of these individual joints, how things should be operated from a waterproofing perspective, as well as from a air infiltration perspective. All those details could be easily analyzed and then also put into place following the instructions that were made from SketchUp's layout application. Going a bit further, this shows a little bit of the detail of some of the air sealing. We knew infiltration would be a really big part of this building's performance. So finding every possible way to identify where air could come out or go in and how to reduce that where it was not wanted is really critical to the performance. Now, in practice, you don't just have an infiltration value or a leakage. You actually need to define a target, and you need to test that target using a blower door test. Now, blower door tests have been around for a couple decades now, but it's really cool to see one in progress. And in this case, looking at the overall area of the envelope, following the passive house principles, we were able to develop a goal, which in this case was 530 CFM at 50 pascals. And if you look at the final blower door results, after depressurizing the house, after spending a lot of time going through every one of the construction details from a ceiling perspective, air sealing perspective, this is exactly what was delivered. We beat the goal and passed at 515, which is under the 530 CFM goal. There are two other parts of the performance data stream, and those are understanding and monitoring on a continuous basis the performance of the building itself. So what I mean by that is, what are the ways in which we can look at the building over time and understand the impact of the outside temperature and outside humidity on how the building feels on the inside? Sure, you could talk to the occupants and get a feeling for that, but one of the unique parts here is we were able to develop a monitoring system specific to this house to be able to measure in 3 different parts of the building and then compare that to the local airport, which I think is 3 or 4 miles away. So get a very close set of external validated data as well as internally measured data and use them to compare. So it's almost 9 years of operation now. And just to give you an idea, this is a view of the house unoccupied. This is from one of the earlier years, but in an unoccupied basis, in the brutally cold winter in the Midwest, you may have -20-degree temperatures on the outside, but the house by itself, and this is the important part, without heat, is able to maintain a steady state of 50 degrees. When it's sunny, which are each of these individual little peaks in pink, those temperatures can rise to 55 or 60 degrees. And again, that's unoccupied. Since then, when you add appliance loads, when you add human loads, people that are in there as occupants, that temperature level goes up by about 8 to 10 degrees. So it's absolutely possible to have a building that is continuously operating without having mechanical heating in the wintertime. The maximum delta we've ever seen in this house actually exceeded the 70 degrees. The highest we've ever seen is a delta of almost 90 degrees Fahrenheit. So that's the temperature difference between the inside and the outside, just to give you an idea of how extreme it can be. And the flip side of this is not just the winter, but actually understanding how the building operates in the summer. This is a set of summertime data. You can see the gray curves showing the daily peaks. These are dry bulb temperatures. It's not feels like temperatures. So the dry bulb temperatures might go into the 90s or even peak above 100 degrees, but there's only a long-term trend within the space, which is eking upwards slowly but surely. And that's that tunnel, which is an untemperature controlled area. And below that, the living room and the upstairs, to give metrics of the downstairs versus the upstairs within a very tight band. I'm saying between 73 and maybe 77 degrees Fahrenheit. So it's particularly comfortable. You can see the impact of the outside sun. You can see a shift associated with the thermal mass and when that mass heats up and then releases its heat into the space. But overall, a very nicely temperature controlled space, which again, has no active air conditioning. Now let's look at cost. Many people have asked, okay, drill in for me and help me understand how you can deliver a building that is this performant. Surely it has to be higher cost than, let's say, a traditional stick-built construction. And the answer is no, it's not. It's about 9% cheaper. And so in this case, this building happened to be self-performed by the owners. And so some of that contractor markup, of course, goes away. But even with that in mind, look at the areas in, as we spoke about before, with finishes in particular, where what normally would be nearly half the budget of the building, that finish component scales down to less than 10% of the build cost. Things like the enclosure become a larger portion. This is an underground house. So we're using the actual benefit of the soil to be able to keep the house core temperature low. That also has a certain amount of enclosure cost to it, especially because the house is built out of concrete as opposed to a stick-built wood construction. Foundation is marginally higher, again, because it's an underground house, but the big components in terms of cost savings are in finish side and also the mechanical and plumbing side. A little bit more about that. The total amount of piping in this entire project, that is the total run length of all the pipes that are actively bringing water into the space, is less than 50 feet, 16 meters. How is that achieved? The reason it's achieved is that the 2 bathrooms in the space are right next to the mechanical room itself. So when hot water is produced in a domestic hot water system, which is a point of use electric system, that hot water is generated on demand, and it has a very low amount of distance it needs to travel to be able to be used in, for example, a sink or the shower head or the bath. So there's not a lot of heat that's sitting in the house waiting to radiate into the space. It's produced and then it's used, and it's a very short time difference between the two. Even then, it's on demand, and so there's no ongoing heating or cooling of the water at the time at which it's not in use. The last piece of this puzzle is really understanding the electric consumption. So what Sterner Design specified was a set of collection tools to be able to look at each individual circuit in the house and to determine what is the amount of energy that's being consumed in watts during that time. So effectively, if you were to open up the entire breaker panel, there are actually 2 breaker panels, every individual circuit has this clamp on it, and the clamp sends data to the E-gauge system. The E-gauge system will provide the exact graph you're looking at right now. If you go to iowanest.com and you click on data, you can see that electric consumption tracking directly. But one of the things that you walk away from as you're looking at the overall building's performance is there are very, very few ongoing loads. In fact, if you look at the overall amount of cost in terms of operating the building itself, we're talking less than $30 per year. So there's a very low cost associated with actually operating the building. And that is specifically due to a low amount of these perpetual loads. The refrigerator, for example, consumes 28 watts. You can click on the refrigerator button. You can see exactly when the condenser's on for that, and you can see when it cycles back off. And that's a load that continues throughout the entire year. So the E-gauge is a great way to be able to look at this building and see it over the course of a broad period of time, both at the micro level, show me the last couple of minutes, as well as the macro level, show me the last year's worth of data to understand how each circuit operates. And with that, a picture of the final product. This is the Iowa Nest itself. And I want to make sure we have time for questions. I think we do. Kelsey?
Thank you so much, Peter. Yeah, no, absolutely. We have some time left for questions. We'll visit the chat here in a few minutes. Again, if you have any, please add them at this time. And if we, for any reason, don't get to any today, then we will definitely, or you have them post presentation, you can always email us. I'll put the email here in a minute in the chat. But Peter, that was incredibly exciting. I wrote down so many things that I was just wowed by. So the corners thing, that was I had never heard of that. That is very cool.
It was a surprise to us too, to be very candid. You know, we looked at a number of these different design options, and it took the process of this integrative process of looking at it from the design lens, but also looking at with the owners, in consultation with the owners, and with a number of different general contractors, and saying, you know what, the cost of this is driven not by the amount of square footage, it's driven by the amount of corners that are in the space, because of the complexity of how do you reinforce the corners, how do you reduce things like blowouts, which happen when you're running insulating concrete forms. And so this became a much more linear process. And the bracing became more linear, the backfilling became more linear, the waterproofing was reduced by going with less corners. The complexity of the roof system was a lot simpler as well. A lot of things got simpler in the process of reducing corners. And it's not something I would have normally seen from other projects.
So since this project, has that just kind of been a consideration then with recommendations for additional designs? I mean, I know this was one architectural firm specific, but with your team sharing, like for instance, using Sefaira.
Yeah, it's definitely been one of the
yes.
simplicity is important. And you want to make things as simple as possible, but not any more simple than that. So finding that sweet spot is the result of iterations, the result of testing, it's the result of actually trying out the design. It is challenging as much as, we've seen just thousands of projects that we've directly been involved with. The ability to test it out and to kind of suspend your disbelief and try it out with one project or one design option next to another. That's the only way you can, in sum, be able to figure out if the design option is better than the other ones you're considering. So
yeah, absolutely. Well, that actually kind of brought me to a question. So we looked at this from the initial design stage, but I'm assuming that you've probably seen this used for a lot of renovation projects as well.
We've seen this, Sefaira is used globally. And so the tool itself is designed for use in any climatic condition and also any type of building type itself, so how the space is being used. Renovations are a really interesting problem because the majority of the building stock out there, that we'll have by, say, 2050, exists already today, right? When we put a new building up, it's depending on the geography we're in, it's rarer for us, for example, in Western Europe, you may not remove a building to its bones. You may renovate it to be able to use it in a different fashion. So renovation has its own specific set of questions. One of the bigger questions there is, what is the composition of my wall, or what is the composition of my roof? Am I allowed to do things within the historic preservation to be able to make changes to the glazing? Many of the buildings you go into that are being renovated, they may have single glazed window units, very poorly insulated window units, simply because nothing better existed at the time, or it was too cost prohibitive when the building was built 100 years ago, or even 50 years ago. With that in mind, how much of that structure can you keep? How much do you need to go back to bare bones and rip out in order to be able to build at a higher performance level? And so other strategies often get looked at there. In a renovation, you might be looking at strategies that are more interiors focused, and ways in which you can change the layout of the space, maybe reduce your mechanical requirements. As I said, going back to the principles of reducing load. And in certain parts of the world, you have permission to do things like provide rigid insulation across a portion of your building on the exterior. So it's like putting a warm blanket on the exterior of the building. And in so doing, you can improve and solve some of the water penetration issues, solve issues related to air infiltration, and make it a more habitable space. But you may not, for example, be permitted to change the position or orientation of the windows. That may have to stay the same, even though you have flexibility in other regards. So I think of it as a dance, and that dance is your partnership with the local authority, the planning commission, to be able to see what works, what flexibility you have. And I always look at it from a design perspective as an engineer, and it's what are the constraints that I have to operate within. And often the more constraints I have, the better of a design we're going to come up with, because those constraints can shape what we are and are not able to do. And then you can use software like Sefaira to test out what the options will look like and come up with the best two solutions and let the owner choose the one that's going to rule the day.
I think a renovation store may be our next presentation. That would be very neat to see. So let's see. I don't see any other questions in the chat. Let me see if I've got any more. Like I said, I wrote down so many things to come back to. The low maintenance over time. That was worth noting.
Yeah, I think maintenance is it's one of these questions where you need to understand the owner's belief system. And some owners have no interest and really are detached from maintenance costs because they may be developing the building to flip it, and then it's somebody else's problem. So the first cost may be the most important factor. But I think increasingly, especially in certainly the last 5 years, you're seeing a move towards more of these owner-occupied spaces, and there the alignment of the incentives is closer. So it might be a triple bottom line thing where I'm not just interested in the first cost to build the building, I'm actually interested in the ongoing maintenance and operational side. And how do I take that sum of actions and reduce that as much as possible? And sometimes that leads to very interesting geometric outcomes.
Very cool. So for the reanalysis portion, how long do you think, so I know you showed data over time, when they've gone back and taken analysis of the finished product. How long does that normally take? Is it something that they can pretty much go in, run a few tests and get back results within a short period? Or is it literally sort of a tracking throughout the year to pinpoint?
It depends on what you're trying to test. So there are ways, for example, the best litmus test, if you want to look at it that way, is you will get a bill, or the owner in this case will get a bill for electricity usage for being tied into the grid. That's the biggest test out there. So what's the number on the bottom of that statement? And how does that compare with the amount of energy that was expected to be used in that space? The separate piece would be looking at the E-gauge monitoring, which really provides this hyper chronological data, right? So you can dial in, you can say, what's happening in the last 10 minutes of usage within this building itself. But it gives you a view of, for example, you can see the compressor start on the refrigerator. You could see, for example, domestic hot water that might be used right now. In the wintertime, you'll see whether or not things like fans are on from the energy recovery ventilator, or whether or not one zone in the building has electric flooring that's turned on. Those things are very easy to see, but that's a very myopic, focused view. The interesting thing is when you zoom out and say, okay, well, what was our budget for kilowatt hours to be consumed by this building? Well, we know what the square footage of the building is. So we can use those two metrics, right, the kilowatt hours and the square footage, to give us our EUI, or energy use intensity. And really the way to think about it, it's almost like a miles per gallon, but for a building, right? Or kilometers per liter for a building. That's giving you the efficiency of how far you can run, how much that energy is required to operate that building. The building itself is not changing. The geometry of it is not changing. The use you might have more people in the building. You might have fewer people in the building. But if the energy is moving up and down with that progression of people, then you could start to test, well, what happens if? And then you can actually run analysis with Sefaira using the data that you have and compare those two and say, are we off Is our actual building as designed off from the design value? And the reality is that even if you're within, heck, you can be within 10% of reality, 20% of reality, and that's still great. Our values tend to be even tighter, more tightly correlated, but the point is to get the direction right. Can't deliver a net zero building or a climate positive building if you haven't set the right trajectory for yourself. And those were things that were set when you had massing and orientation and the glazing ratios. All that stuff was stuff you did in conceptual design. So if you put your time and effort into design there, it yields results like you're seeing right here.
Emphasis on using this in the design process. So
Yeah.
no, that's exciting to see that. I love the journey, the story from the beginning to the end, and being able to see it all come together. You sort of takes me then talking about the journey. So what is kind of the roadmap, or what's next for Sefaira?
That's a really good question. So a lot of there's been a lot of focus recently on making the tool as accessible as possible for as many people that are using the broader SketchUp ecosystem. So that means reducing any friction that exists in the process. How deep can you use it in the process is always something people always want to push the development farther and deeper and into more kind of more design development angle. But I come back to this first principle, and this has guided us for probably 20 years at this stage, which is this broad idea of if you can make change, if you can test things early and test them as iteratively as possible with as least friction as possible, that's what delivers the best outcome. What I'm saying is the ability for you to try out different geometries and different parameters, different permutations of those early designs, which is well in line with the conceptual modeling practices that are popular today. The more of those things you test out, you can see what the outcomes are. And that's when you say, you know what? Here's the results of our brainstorming. These are the set of options we are not interested in. These are the ones that are a subset. These are ones that we really can focus on that could be potentially good candidates. Let's refine those. And so that gets designers onto the best track possible, gives them the best start possible as early as possible. Why early? Because the earlier you do it in the design process, the less rework you need to do. And so much time is taken up in architecture, in engineering, in rework, in having to do something over again based on a change in design intent or input or field conditions. To the extent you can reduce that amount of rework, thoughtful design, the designers that use Sefaira, they are incredibly instructive and inspirational. And there's tons of examples on the blogs of people who have used the applications to deliver really world-class projects. But you'll notice one thing in common, and that is that they design early, they design often, they put the effort onto conceptual design because they know that's where the outcomes are going to be the biggest. You don't think of sustainability as the thing you do at the end of a project. It's too late. Too many things are baked in at that point. Sustainability is something you start at from the very, very beginning. And those companies that are leading the charge from a sustainability and an energy efficiency perspective, they have that baked into their DNA. That is their common thread.
Making the right stepping stones from the very beginning.
That's right.
Awesome. Well, we don't have any more questions. Is there anything else you'd like to touch on before we wrap up for the day?
No, that's great. Any other questions? Feel free to reach out to ArchVision and myself. Happy to go from there.
And I am putting our email address in the chat. So if anybody, like I said, does have any questions, please reach out to us. We will share the recording once it's available. And Peter, it was an absolute pleasure today. Thank you so much for sharing, presenting, and we look forward to having you back.
You're very welcome. Take care. Bye.
Bye-bye, everybody.